everyone, I am Vaishali Rastogi. Here I am going to represent the topic of Introduction of Arithmetic Logic Unit in the subject Computer Organization and Architecture. So, here we will study about first the number system, a system for representing a number of certain type. Okay, here we have only single line to define what is number system. Again, if I talk about normally we use numbers like 1, 2, 3, 4, 5, 6, 7, 8 to represent our words in the normal digital form. Okay, so in human language we are having from 0 to infinite, whatever number you want to consider you can consider. But in digital system, in computer organization, we are having binary, octal, decimal and hexadecimal kind of representations. What is these kind of representation we will learn in our further PPTs. First of all, we should know that there is some base. What is base? Base is basically when we represent that this number belongs to particular category. Like for binary, we are having base 2. Whenever we represent any binary number which is having the symbol of 0 and 1. Okay, so any possible combination of 0, 1, it is basically belongs to the binary. And how we will represent? We will represent by using this base. Okay, base 2. Whenever we see that there is a base 2 in any number, then we can say that this number belongs to the binary category. As well as the octal. Octal is having the base as 8 and the symbols are 0, 1, 2, 3, 4, 5, 6, 7. 0 to 7. Okay. As in decimal we are having, we all know that 0 to 9. These are the common numbers. And base in hexadecimal, we are having base 16. Okay. In 16, there is something new added. 0 to 9 as well as A, B, C, D, E, F. How we will use these numbers to represent our digits, we can see in this diagram that we are having 0 to 15 in decimal. How we can write 0, 1, 2, 3, 4, 5, 6 in binary? Basically, 0 is represented in 40 and 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. These all the representation of these digits in binary. As well as all these digits can be represented in octal too. Okay, so 7 is in decimal, we can say 007 in octal. But when we come to 8, what happened? 8 we cannot represent 8 as a 008. Why? Because we are having only limit up to 7. So here in this case we will write 8 in a partition. Like again we will so in up to 7 we will write 007. Now whenever we represent 8 we will start it again. We will write again 10, 1, 1, 1, 1, 2, 1, 3. So we have count only from 0 to 7 as the initial count, and up to after the 7 we have this kind of representation. For representing 15 we are having 017. Okay, in hexadecimal how we can represent? Up to 9 we can represent like 0009. Whenever it come to 10 we always represent 10 as a A, 11 as a B, 12 as a C, 13 as a D, 14 as a E, 15 as a F. Okay, so this is the basic number representation in the form of decimal, binary, octal and hexadecimal. Now, we will see that how we can convert these numbers from this to this to this, and vice versa. So, number conversion is basically we can convert the number of binary into octal or octal to binary, hexadecimal to decimal, decimal to hexadecimal, or hexadecimal to binary, binary to hexadecimal. All these conversion we can do and we will see step by step. Like first we are having binary to octal. Okay, so we are going to convert the binary number into octal number. How we will do? It is very easier steps. We have to just do only group of 3s. We will group digits in the 3s group, and if whenever we are having any number which is not divisible by equally in 3, we will just add 0 in front of the digits. Like in this example, we can see that we are having 10101001. Now we are going to group these digits into 3, like these 3. Then we will group another one, and now we are having a single one left over here. So we will normally so we are having only 1 here. Now we will just add 2 0 in front of 1. so that we can group this one as a 3 digits. Okay, so in 101 we can say in octal we are having 5. 101 is basically is 5 and 010 is basically 2. 001 is represented as 1. So what is the answer? 125 base 8. Okay, so 8, here you can see that this is a representation of octal number. So this binary number, because this is representing as a 2 base, is converted to the octal and we can have 125 base 8. Okay, now we will see the vice versa process too. Octal to binary. So for each of the octal digit, write its binary equivalent. It is as simple as that. We will just write every binary equivalent for every octal digit. Okay, whenever we are having 2, 5, 7, 8 to convert it into binary. So how we will do that? We will just make a separation of 2, 5 and 7 and we will convert each single digit into the binary. So 7 in binary we can write as 111, 5 in binary we can write as a 101, 2 in a binary we can write as 010 and we will combine all these digits to represent our binary number of 257 base 8. Okay, so we are having 010, 101, 111 as a binary. Okay, so this would be our output of binary octal to binary numbers. Now we are going to convert binary number to hexadecimal form. How we will do that? We have only 2 or 3 steps to do so. Firstly, let's suppose we are having this digit. So what we will do? We will just make 4 digit combinations. Okay. So last 4 digit, we will start from here. Now again, we are having only 10. So what we will do? We will just add 0 at the most significant end. So we will add 20 over here. Okay. Add 10. So now we are having this digit divided into 4 parts. We will just write the hexadecimal number for equivalent to each combination. So 0010 in hexadecimal we can write as a 2 and 1011 in hexadecimal we can write as a B. 1011 in hexadecimal we can write as a B. So our main output is as 2BB base 16. Okay. So next we will do as a vice versa process again. Hexadecimal to binary. Okay. So for each of the hex digit, write its binary equivalent. As simple as that. We don't need to follow any long rules. We just need follow only one thing, that we will write hexadecimal we will write binary equivalent to each hexadecimal digit. Okay. So for 2 we will write as a 0010. For 5 we will write as a 0101. For A, we will write as a 1010, or for 0, we will write as a 4 zeros. We will combine all these digits and we can make the hexadecimal number to binary number conversion. Okay, so hexadecimal is having base 16 and binary number is having base 2. So we can say that this number is in hexadecimal is equivalent to this number in binary. Okay, so next we are having octal to hexadecimal. We are having the same rule. We will just divide the digit in a singular form and we will convert into the binary. Then binary to hexadecimal. We have only this process here. So let's suppose we are having 635.27 base 8, means this number belongs to octal category and we have to convert into hexadecimal. First step, we will do octal to binary. Then this binary number will be converted into hexadecimal. Okay. So 635.27, we have seen that how we can convert octal to binary. We will write binary equivalent to each digits. 6 in binary is 110, 3 in binary is 001, 5 in binary is 101, 2 in binary is 010, 7 in binary is 111. So now we will do binary to hexadecimal. First of all, we have to make 4 groups. Okay. So 4 digits group is basically 1101 first group. Another one is basically 1001, and now we are having only single one here. So we will add 3 zeros. So 0001, we have added 3 zeros here to make the combination of 4 digits. Now here we can see that as in binary we are having 010, and now we have to make the group of 4 digits. So 010 and this one. Okay. Now we have left. Now we are having 11. So we have to make the 4 digits group. How we will make? We will add some zeros over here. Now first group we are having as 0001, which is in binary basically 1. So we have written 1. Next group we are having 1001, which is represented as 9. Next group we are having 1101, which is represented as in hexadecimal, is basically D. Now we are again having 0101, which is the representation of 5. Now next we are having 1100, which is the representation of C. So our final answer is basically 19D.5C in hexadecimal. So this number in octal can be represented as this in hexadecimal. Okay. So we will see again the vice versa process. Hexadecimal to octal. Okay. So again we will follow the reverse process. We will basically going to convert all the hexadecimal number to binary and then binary to octal. Okay. So hexadecimal to binary and binary number to octal. We will follow these steps. So first of all, we are having a hexadecimal digit as A3B.7 in the base 16 means hexadecimal. So we have written. So we are going to write binary equivalent for each digits. For A, we are having 1010 in binary. For 3, we are having 0011 in binary. For B, we are having 1011 in binary. And for 7, we are having 0111 in binary. Now again, the process, we will make the group of 3 digits. Okay, the first 3 digits we are having as 011, then again 111, again 000, again 101. Here we will make first 3 digits group 011. Again we are having 1 left. We have to make the group of 3 digits. Now we will do 1 and we will add some 2 zeros here to make the group of 3 digits. So for first group we have written for 101 we are having 5 in our octal format. Next 000 in octal format is basically 0. The next 111 111 in octal we are having as 7, and 011 in octal we are having as 3. Okay. Now next 011 in octal we are having as 3, and 100 in octal we are having as 4. Okay. So our final answer is basically 5073.34 in octal. So for this hexadecimal digit we are having the equivalent octal output. Okay. So next we are going to convert the binary number to decimal number. This process is having some rules, like converting from binary to decimal is done by multiplying each digit by its weight and summing. Okay. So let's see with this example. We are having the digit as 11011011. We have to convert in the decimal format. How we will do? We will just multiply with the base, as well as we will just going to add all the output in a final form. So let's do it. For first one, 1 is going to multiply by 2 to the power 0. And again, another next digit is going to multiply by 2 to the power 1. For another digit, we are going to multiply this digit by 2 to the power 2. And again, next for next digit, we are going to multiply by 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power 7. we will multiply each digit with some 2 to the power in the sequence. And here we can see the final calculation, that multiplying by 1 into 2 to the power 0 is equal to 1 multiplied by 1, and we are having as a 1 output. And again 1 into 2 is 2, 0 into 4 is 4, and so on. Okay. Now, and in next step, we will just add all these numbers, and the final output is as 219. Okay. Addition of all 1, 2, 8, 16, 64, 128 is we are having as 219. Okay. So, in a decimal, we always represent as base 10. So, our final output is basically 219 base 10. This is the equivalent number to this binary number. Okay. So, this is our binary to decimal number conversion. Next, we are having the vice versa process as a decimal to binary. So, let's do it. Here we have some another kind of approach, like we have to divide the integer number by base 2. Okay, whatever number we are having to convert in binary, we have to divide that number with the base 2, and then we will store the quotient and the remainder in a separate place. So, let's do this example. We are having 20 in decimal and we have to convert this number into the binary. We will divide 20 by 2. And as a remainder, we are having 0. Next, we are dividing 10 by 2 and we are having remainder as 0. Again, we are dividing 5 by 2 and remainder is having 1. Again, we will divide 2 by 2 and we are having remainder as 0 and quotient as 1. So, we will just write in the reverse form, okay, from here to the top. We will write in this sequence, like first is 1, this one, then 0, then 1, then this 0, and then this 0, and this is our binary format. Okay, so here we have converted 20 in decimal into the binary format. As we can also, so we are going to move for the next PPT. Now we will move to. Now we will going to move for our next topic. It's basically the first complement. So how we find the ones complement for any given digit? Basically, we do nothing. We have only one rule, that all the ones goes to the 0 and 0 converted into the binary. Again, all the 1 is converted into the 0 and all the 0 is going to convert in the 1. So let's do with this example. We are having the digit is 1 1 0 1 0 0 1 0, and we are going to take the we are going to find the ones complement. So we will just make 1 converted into 0 and 0. We will convert 1 into 0 and 0 in 1. So let's do it. For this one, we will convert 1 into 0. For this one, we will convert 1 into 0. Now we are having 0. We will convert this 0 in 1, and again for 1, this one, we will convert 1 into 0, and again 0 will be converted into 1, and again so on, 1 is converted into 0, and 0 is going to convert into 1. So this number is the first complement representation of this binary number. Okay, this is a very simple process. Whatever digit we are having in the combination of 1 and 0, we will just convert this number 1 into 0 and 0 into 1. This is the representation of first complement. Next, we are going to see what is 2's complement. 2's complement is very simple, that we can see that 2's complement of any number, we only need to find the 1's complement and add 1 with this 1's complement. Let's do with this example. We are having 000 10100. This is representation in binary number. You can see that because we are having only combination of 0 and 1. Now we are going to find the 1's complement of this given digit. For all the 0, we are going to convert into the 1. Like for this 0, we have converted as 1, 0, 1, 0, 1. And this one is going to convert into 0. Again 0 into 1, 1 into 0, 0 into 1, 0 into 1. So we have got the first complement, 1's complement of this given binary number. Now we are going to find the 2's complement for this number. So we will just going to add 1 with this given 1's complement. So as you can see that we have written this number as the same and we are going to add 1. So let's see 1 1 0 carry 1 1 1 again 0 carry 1. So 1 0 1 and again so on 1 1 0 0 1 1 1 1 1. So this is the representation of 2's complement of the given binary number. Okay, whenever we want to find the 2's complement of any digit, we need to learn only one rule, that take the first complement of that given number and add 1. This is the simplest rule of 2's complement. Next, we are going to learn about the addition of simple 2 binary number. Okay, it is very simple process. We have seen that binary number are the combination of 0 and 1. Okay, so whenever we have any calculation, all calculation comes among 0 or 1. Now we are going to see that if we add 0 to 0, what we can have as a summation as 0. Whenever we add 0 plus 1, we can have our answer as 1. 1 0 answer is 1. Now whenever we add 1 plus 1 means 1 plus 1. So here we are having 1 plus 1, we will have the output as sum as 0 and we will are also having 1 carry which come here, but there is no digit, so we will write only like that. Okay, so here this is the sum and this is the carry. Okay, so how we now we are going to see that how we can add 2 number with the using half adder and full adder. So we are going to learn first about the half adder. Basically, this is the block diagram. Here we are having 2 input as A and B and 2 output as sum and carry. Earlier we have seen that whenever we add 2 digit in the form of 1 and 1, we are also having 1 digit as a carry. So this carry is going to represent that digit. So half adder is a combination logic circuit designed to add 2 single digit numbers. Okay. It contains 2 input and 2 output. Output is basically named as sum and carry. And this is the complete block diagram of this half adder. How it works, we have to see that. First of all, we are going to write the truth table for the half adder. Here we are having 2 input. Like inputs are, we have renamed that A and B. All the possible combination of A and B can be 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So what we can find as output, we will see whenever we add 0, 0, we having sum 0 and carry as a 0. Whenever we add 0 and 1, we always have 1 as a sum and no carry. Again 1 and 0, whenever we do the addition of 1 and 0, we always have 1 as a sum and no carry. But in the case of 1 and 1, we have, I have already told you that 1 plus 1, we have 0 as sum and 1 as a carry. So here we have written this 0 as sum, this 0 and this 1 as in carry. Okay, so this is the truth table of that particular half adder. So we are going to create the K map for sum and carry. So these are the K maps. We will create for carry first. We are having 1 at the combination of A and B is 1. So here we are having the combination of A is 1 and B is 1. So this combination will have 1. Again for this sum we will going to, for again sum we will create the K map as here 0, 1 A's value and B's value also 0, 1. So whenever we are having 0, 1, A is 0 and B is 1, that we are having 1, and A is 1, B is 0, A is 1 and B is 0, then we are having 1 here. So we will find the equation for that, carry and sum. For carry, we are having only one, that A is value 1 and B is value 1, hence we have AB. Here we are having 2, 1, so for this one we are having A and B bar. Okay, so we have written A and B bar. For this one we have A bar B. So A B bar plus A bar B is nothing but the A XOR B. So we can create our circuit with this particular equations of carry and sum. So we are going to take two input A and B, and we will have two output as sum and carry. How we can decide that what kind of gate we are using here? From this equation, that we are having one XOR gate, one AND gate. So one XOR gate, one AND gate. So XOR gate, as we have input as A and B XOR, we are going to have our sum on this output. Next we are having carry. For carry we are having only A and B, means A and B. So AND gate, between those two input and in output we will have C, means carry, as the output. Okay, so this is the complete concept of half adder. We can sum यहाँ के बाद next है. So in next PPT we are going to learn about the full adder. What is full adder? Full adder is basically a combination logic circuit designed to add two single bit number with carry. Only one difference we are having here, in full adder and half adder. Here we are having two input, but again we are having one carry bit. Okay, so this is the block diagram of full adder. And here A and B, similarly the input digits, and C in is basically a carry input. Again we can have sum and carry in an output, but we will write C in because this is the input carry and this is the output carry, so we can also write as a C out. Okay, so we will see how this full adder will work in the next slide. Adder of in this circuit we can see that we are going here. First we will see the truth table. Okay, so we have two input as A and B and one carry input as C in. The all possible combination of A and B is basically 0 0 0 1 1 0 1 1 for carry 0 and 0 0 0 1 1 0 1 1 for carry 1. Okay, we will see what we can have as an output, that whenever we add these digits as a 0 0 0, we will have 0 in sum and 0 in carry. 0 0 1 means 0 0 1, so it is 1. Basically we are having 1 and a sum and no carry, so it is 0. Again 0 1 0 is basically as a sum we are having 1 but no carry, so it is 0. But here in 0 1 1 for this one, here 0 1 1 1 1 again in sum 0 and in carry we are having 1, so we will write 0 0 in sum and this carry will go into the carry part. Again here we are having 1 0 0, 1 plus 0 0, 1 plus 0 1, 1 plus 0 1, basically in output we are having 1 and carry is 0. Again now we are having 1 0 1, 1 0 1, so 1 1 1, so 1 0 1 1 1 as sum as 0 and carry as a 1, so sum as 0 and carry as a 1. Again 1 1 1 1 0 carry as a 1 and 0 0 0 carry as a 1. Again triple 1, we are having this case, triple 1, this. In this case we will have 1 as a sum and 1 as a carry. Okay, so 1 as a sum and 1 as a carry. So now next we are going to create K-map for this sum and carry. For sum we will write all the 1 at the place of where the one where we are having 1 at the place of, यहाँ से cut, So we are going to create K maps for sum and carry. We will write 1 at the place of this, 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 and this. Whenever we are having 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, and triple 1, 1, 1, 1. These 4 1 we are having here. For carry, again we are going to create the K map. Here we are having 1 at the place of 0, 1, 1, 0, 1, 1, 1 at the place of 1, 0, 1, 1, 0, 1, at the place of 1, 1, 0, 1, 1, 0, and again triple 1, 1, 1, 1. So all these 4 1 we can write here. Now we are going to find the equation. Whenever we have this kind of combination, we always write as a bar B C in plus A bar B C in. इसको कट कर देना. So we are going to write the equation for these all possible combination of 1 and for this. So we are having as C in XOR with A XOR B and AB, AC in and BC in for this combination. Now we are going to create the circuit depends on the equations. We are having 3 input as A, B, C in, A, B, C in, and in output we are having sum and carry, sum and carry. So we are having this equation. First we will see the equation of sum. Equation of sum is saying that only XOR operation between these 3 inputs. So all these 3 input will go in a XOR gate. And in this case, we are having 3 AND gates here. So we will apply 3 AND gate between AB, AC in, BC in. Means AB, A, C in, and C in and B. C in and B, last one. And OR gate between all these 3 outputs. So we will just apply one OR gate among all these outputs and we can have our C out, means the main carry as an output. So in input we have taken 3 input and in output we are having sum and C out. So this is the concept of full adder. Now we have learned for today we are going to end up to this topic. Okay. In next video we will see the further concepts. Thank you.